right, our third speaker this morning is Sergey Neshveyev from the University of Oslo, and he will speak about KK-duality and quantum hyperbolicity.
Thank you, and thanks to the organizers and everyone for having me here. So I will talk about a joint work with Francesca Ricci and Dimitris Gerantikianis, and it will be about some explicit construction of KK-duality, which is also known as sometimes called as non-commutative Poisson-Poisson-Poincare duality. And the formal definition is as follows. So we start with two separable sister algebras A and B. They are called KK-dual with dimension shift I if there is a K-homology class, delta, and a K-theory class, small delta, satisfying these properties. So if you don't know what KK classes are, don't worry, everything will be very explicit. It is some homology theory, but the way to think about it is that these are more general versions of homomorphism of sister algebras. So you can think of delta as some sort of generalized version of homomorphism from AB into C, and the small delta as some generalized version of homomorphism from complex numbers into B tensor A. And these are kind of duality conditions, the usual duality conditions for say vector spaces or objects in some monoidal category. So there are two main sources of KK-duality for non-commutative sister algebras. One goes back to Kasparov back in the 80s, who proved that if you have a compact Riemannian manifold, and you can see that algebra of continuous functions of this manifold M, then it will be KK-dual to the graded algebra of sections of the Clifford bundle over M. And one of the duality classes is given by the Dirac operator, and there are various generalizations and various consequences of this result. So it's not only just for commutative algebras you can get some duality, but also by some deformation. Say this way you can also get KK duality for non-commutative tori, but still somehow it's all deals with some versions of Dirac operator and the dual class. And then there is another version of another source of duality, which seems to be quite different, and the precise relation is, I think, still not very clear, which is due to Kamenker-Putnam and then in full generality developed in their work with Whittaker. And there the source of duality is some sort of hyperbolicity. So what they prove is that if you start with a Smyov space, and again, we don't need a formal definition. I will give a concrete example. Everything will be very explicit, but roughly you are given a metric space, if you want a manifold, and you have a hyperbolic transformation. And hyperbolicity means that at least locally, you can decompose your space into direct products that in one direction you have contraction, and in the other direction, the inverse is a contractive map. And then you can associate these sister algebras, and they turned out to be KK-dual. As I said, in the next slide, I will give a very concrete example. So a closely related result is the result of Emerson, where you start with a free group, and you consider its free group action on its boundary, on the n-compactification of the ends of its Kelly graph, and then this cross-product algebra turns out to be self-dual. So as a very particular case, and this was the starting point of this duality, which was done by Kamenker and Putnam, they proved that if you have Kunz-Kricker algebras corresponding to matrix A and to its transpose, then they are KK-dual. And in a very particular case, this means that say Kunz algebra is self-dual. So how does it work? So as I said, everything will be very explicit and concrete. So let's look at this case of Kunz algebras. So we fix a number, natural number m larger than 2, and define the Kunz-Toeplitz algebra and Kunz algebra as follows. So consider full Fock space. So you start with m-dimensional Hilbert space, and consider a direct sum of its. Oh, sorry, this is misprint. So this is nth tensor power, not the usual power, but nth tensor power of Cm. And we have a creation operator. So the operators which simply take a vector in this space and tensor it with an element of our fixed basis. By definition, the Kuntz-Toeplitz algebra is the sister algebra generated by these operators S1, Sm. This Toeplitz algebra, one can easily check, contains the algebra of compact operators on this full Fock space, and the quotient is the Kuntz algebra. And say that these are the algebras associated with just the shift on the so the shift space on n letters. And the classes, the dual classes, are represented as follows. So the fundamental class is given by homomorphism from OM, from Kuntz algebra with itself into the quotient of the algebra of operators on the full Fock space by the compact. So in addition to operators of tensor on the left, of the left creation operators, you could also consider the operators of tensor on the right creation operators. These two kind of operators commute. If you consider their adjoints, then they do not really commute with the adjoints, but they almost commute. So if you take any such operator and consider an operator of tensor on the right, and take the commutator with the adjoint, then you will see that you get a rank 1 operator. So at least they commute modular compacts. As a result, you have a well-defined homomorphism from this tensor product into this quotient. And this represents one class. And somehow the existence of this class, sort of, it's a manifestation of hyperbolicity of the shift map from the of the shift on n letters. And the dual class is given by explicit homomorphism from the algebra of functions on the real line vanishing at infinity, which we think of functions on the circle vanishing at point 1. So to construct such a homomorphism, you just need one unitary. So we can extend it to algebra of continuous functions on the circle, and to construct such a homomorphism, you just have to find one unitary in the tensor product. And as such unitary, you can take this operator. One can check that this is indeed a unitary. If we consider corresponding operator in the Toeplitz algebra, then it will be only a partial isometry. But when we take the quotient, that it's really a unitary. And these turn out to be dual classes. So what I'm going to explain is some sort of quantum relative of this result. Although this is already a non-commutative duality, we'll give like a quantum version of this non-commutative duality. In fact, as sister algebras up to KK equivalents, they will be exactly the same sister algebras, but these abstract KK equivalents give you no idea how to construct these classes. And this is what the key point is, as I'll explain. And the reason why it should be relevant for the topic of this conference, of two reasons. One is that the quantum symmetries of the things we're going to consider play a crucial role both in the construction of the classes and in the proof of the duality. And second is that sort of the reason why it all works will be some sort of version of or manifestation of some quantum hyperbolicity. So it will be some quantum hyperbolic transformation, although I will not try to formalize what exactly this should be. So if you want some quantum hyperbolicity of some infinite quantum graph. Okay, so let me explain what kind of algebras and construction we're going to work with. And the algebras arise from so-called subproduct systems. It's a generalization of the construction of Kuntz-Krieger algebras, which appeared in works on quantum function theory and also on duration of semi-groups acting on operator algebras. So what it is? So we say that a standard subproduct system is a collection of Hilbert spaces, finite dimensional Hilbert spaces. So for each n, we have a finite dimensional Hilbert space. And the requirement is that at the zero place, we have just complex numbers, dimensional algebra. And then Hn sits in the nth tensor power of H1. And the only requirement is that Hn plus m is a subspace in Hm tensor Hm. So in the Kuntz algebra case, it corresponds to the case when Hm is simply equal to the nth tensor power of H1. Here we require only that this is a subspace, and correspondingly we require that this is only a subspace here. But once you have such a structure, you can do the same construction as we did in the Kunz case. And so we fix on a formal basis. We consider the full Fock space associated with the subproduct system, direct sum of all these Hns, and consider projection on the from the full Fock space, so generated by H1, onto this Fock space corresponding to this subproduct system. And we define again the operators, web creation operators. So we take a vector in our Fock space, we tensor it with EI. This way we can get a vector outside our space, but we project down this full Fock space corresponding to H and get some operator. And then we consider the Toeplitz algebra, sister algebra generated by all these operators, creation operators S1 and M. Again, it's not difficult to see that the sister algebra contains compact operators, and as a result, we can consider the Kunz-Pimsner algebra, the quotient of the Toeplitz algebra by compact operators. Okay. So this is our sister algebra, but before I introduce the class we're really interested in, or we'll be working with, let me explain another somewhat different point of view on this, more sort of algebra geometric or function theoretic, which is as follows. How to think of the standard subproduct system. So another way to look at them is to think of algebra in M free variables, so in algebra of non-commutative polynomials in M indeterminants, and we consider homogeneous ideals in the corresponding algebra. And if we consider the components of these homogeneous ideals, and consider their orthogonal complements in this n times the power, these are our spaces Hn. And this way we can actually get a one-to-one correspondence between subproduct systems of finite dimensional spaces and homogeneous ideals in these algebras of non-commutative polynomials. And this way, one point of view on the sister algebras, and this is how one of the motivations why they appeared, is that when you study them, you sort of study some non-commutative function theory, because it turns out that if we consider, so the algebras which we defined, they all satisfy these properties that these operators S1 as M, they form a row contraction, meaning that this inequality is satisfied. And for all polynomials in your ideal, you have this condition is satisfied. So in other words, what you have is some sort of what the algebra describes is some semi-algebraic subsets of the non-commutative unit ball. What you're doing is you're studying functions on this subset of the unit ball, and the quotient is like functions on the boundary. Typically think as functions on some non-commutative sphere. So the simplest interesting, and this is already a non-trivial and interesting example, because again to study quite some time ago, is just to consider the ideal generated by one polynomial, x1, x2 minus q, x2, x1. So in the case when q is equal to 1, your algebra, your Kunz-Pimsner algebra becomes commutative in two variables, and it's not difficult to show that you actually get an algebra of functions of a three-dimensional sphere, so on the sphere in two-dimensional complex space. And so by varying q, you therefore get a family of algebras which are some sort of quantum versions of deformations of the three-dimensional sphere. Okay, so what kind of, these algebras are not particularly well studied. I mean, people began to study them quite some time ago, but they are fully understood only in very, very few cases. And the case we will be interested in is sort of one of the main points is that it will have a lot of symmetries. And let us formalize what I mean by a lot of symmetries. So we'll be interested not in arbitrary collections of these finite dimensional Hilbert spaces, subproduct system, but we in addition assume that we have a compact quantum group acting on all these spaces. then naturally we say that our system is G equivariant if all these subspaces are G submodules. So we have a collection of finite dimensional representations, and the tensor product respects our action of G. And let us say, just temporary notion, let us say that our symmetry group is large if all these modules Hn are irreducible. So we're going to exploit, so if we have this largeness, we can hope that we can exploit the symmetries of our system to say something about the algebras. So what we're going to consider is probably the simplest thing you can think of, and it turns out already this simplest thing is quite interesting and complicated. So we'll consider only quadratic polynomials. So let's start with just the ideal generated by one quadratic non-commutative polynomial. And we assume that, so the assumption is some non-degeneracy, so assume that the determinant of this matrix, or this polynomial, is non-zero. And we can consider the largest possible symmetry in this case. So one can introduce a compact quantum group of transformations leaving these polynomials invariant. We can start with leaving them invariant, but we can do a little bit better. It's enough to consider transformations which leave this polynomial invariant up to phase factor. And kind of interesting enough, in the classical case, it doesn't really matter much. You don't gain much from adding phase factor, but in the quantum case, you actually can gain quite a lot. So this quantum group can turn out to be much, much larger than the quantum group of transformation leaving literally the polynomials invariant. Okay, but do we really get a large set of symmetries, so in the sense we introduced? Turns out that not always. In fact, we can completely describe when this happened. So this is what I was my former student Eric Habestad did some years ago. So if we consider such a situation where we define the quadratic polynomial, and so when do we have this large group of symmetries? So let us consider the rank 1 projection from the space of all homogeneous polynomials onto this one-dimensional subspace spanned by these polynomials. And it turns out to be that this quantum group of symmetries is large in the sense we define if and only if this projection satisfies the temporally Lip relations. This relation of this form. In fact, in this particular case, these two relations IQ, you can require any of them. The second goes automatically. More concretely, you can completely describe what kind of matrices you get. So it turns out that this is also the same as to say that the matrix A bar is unitary up to non-zero scalar factor. Or you can even very explicitly write what kind of matrices you get. So these are exactly matrices which you can, by choosing a unitary matrix V, you can write in this form. So VA, V transpose. Should be a matrix of this form, and the only requirement is that these numbers are independent of R. And then up to rescaling, we will always assume they're just equal to 1. Okay. So this is so therefore we have quite a large family of algebras, so roughly m half complex parameters, and this is a class of algebras we're going to study. Okay, yeah, well, these are really famous relations, temporary Lip relations. So indeed, for temporary algebra, one knows many things. So one of the things which makes it possible to do combinatorics in this case is the famous formula for the corresponding projections. And the formula itself is not going to be important for us, but basically in this slide, I want to introduce some numbers which will play an important role later. So yeah, whenever convenient, I will. So sometimes I will write things for arbitrary this temporary Lip polynomial, and but sometimes formulas simplify if I consider these matrices, and then I will just do it just to make the expressions a bit nicer. So, like in this case, so we consider a temporary polynomial of this form. Satisfying this property, I said up to change of variables, every polynomial can be written like this. And with this polynomial, we can associate a number q by this property. So we consider the corresponding subproduct system. So remember, the polynomial defines an ideal. Then we take the homogeneous parts of this ideal, takes the orthogonal complements, and this gives us our subproduct system. And these corresponding spaces are projections. So these are by definition subspaces of this n times the power. So there are some projections Fn on these subspaces. So simply by definition, these projections are obtained as follows. So you have to put this projection, one projection corresponding to polynomial in different places, and then take the orthogonal complement of the union of all these projections. So we get these projections Fn, and one knows an explicit recursive formula for these projections. And as I said, for us, more important is all these numbers. So we have, so the things to remember is the number q, which comes from here, and then these q numbers, and then the ratio of these q numbers. Okay. So I said basically this is a starting point which allows you to study this algebras. So I said so if we return back, the main point of this class of algebras that you really have a large quantum group of symmetries, and this is the only class. It's exactly the class of quadratic polynomials for which the largest group of symmetry is large. But what exactly is quantum group? So let me say a few words about this quantum group. But for this, I will need just one more notion. Recall that two compact quantum groups are called monoidally equivalent if their representation categories are equivalent. Again, this can be made very concrete. So we're going back to Woolbridge. One knows that two compact quantum groups are monoidally equivalent if and only if they have free and transitive, if you want, ergodic actions of these quantum groups on one cyst algebra B, which is called the Galois objects. So what free transitivity means, I'm not going to say explicitly, very precisely, but approximately it means the following. So transitive or ergodic means that the action has trivial fixed points. So there are no elements apart from the scalars, which are fixed by a quantum group. And freeness means more or less that your algebra, if you forget the algebra structure but only look at the linear structure, it looks at the algebra of functions on space. So in the commutative case, if we dealt with usual groups and we dealt with commutative algebras, if we have two commuting free and transitive actions, that would just mean that the groups coincide or isomorphic. But it turns out that exactly because you allow to change the algebra structure, so instead of commutativity, you can allow non-commutativity. This becomes non-trivial already for finite groups. So even for finite groups, you can get something non-trivial, and you have non-isomorphic groups which are actually monoidally equivalent. So now I can formulate, say more or less or at least say something about this large symmetry group of our system. So the claim is as follows. So we start again with a temporary polynomial. Remember that we introduce this number q given by this property. And then the following is true. So it turns out that this quantum group of symmetries is monoidally equivalent to uq2, some q deformation of the the group of unitary 2x2 matrices. So in particular, it has a well-understood representation theory. And moreover, this Galois object, which implements this monoidal equivalence, is constructed closely related to corresponding Kunz-Pimsner algebra. So more precisely, it's not exactly Kunz-Pimsner algebra, but it's cross product of this Kunz-Pimsner algebra by an explicit homomorphism. So maybe for those who have worked on it, on such things, that it turns out that very often one has a candidate for our object, and often a difficult task is to prove that this candidate is actually non-zero. You start with an algebra with some generator some relation, but then you try to find or prove in some way that you actually get a non-zero sister algebra out of it. And somehow the subproduct systems give you this algebra for free. So the first result, this monoidal equivalence, was proved some time ago by Mrazinski, but through this subproduct system, you actually get a different proof, as well as a different proof of earlier results of Banneker, Vaz, De Wright, and Bichon on some other monoidal equivalence, exactly because you kind of get for free non-zero representations of your candidates for Galois objects. Anyway, for us, the most important thing is that this quantum group is monoidal equivalent to each other. So it has very explicit representation theory. Okay, so now we're ready to describe these dual classes. So again, we start with.
Category is just AN, right?
Sorry?
The representation category is AN.
Well, it's not quite AN because it's U2, not SU2, but
no,
yeah.
I mean AN in the suffix, so it's not temporary.
Yeah, but as I said, I mean, okay.
Q is a root of unity, right?
No, Q is not a root of unity.
It's not a root of unity?
No. I mean, this Q is between 0 and 1.
Oh.
I mean,
So then you get infinite categories?
yeah, of course. In these cases, we always get infinite categories. What is so here? So even here, when I start with a polynomial like this is a temporary Lie polynomial. Here, I am allowed to take Q, not say a root of unity. But in fact, this is not the same Q which appears here. This will be just absolute value of Q. So this Q will be equal to 1. So, but whether we'll always get a Q between 0 and 1 and infinite category. And, okay. So returning to the fundamental class. Okay, we start with a temporary Lie polynomial. And so again, we can consider two representations of Toeplitz algebra on the full Fock space corresponding to subproduct system by left creation operators and by right creation operators. So in the Kunz case, if you remember, I said that the generators and their adjoints, they compute modular finite rank operators. It turns out that here it's not true, but they still compute modular compacts. So you have these operators compute modular compacts, and as a result, you have a well-defined homomorphism from this tensor product in this quotient. And what is behind this commutation is this quite old estimate of corresponding projection defining the subproduct system. So in some sense, it is somewhere here when already feels that there is some sort of hyperbolicity which is responsible for this. But as I said, I will not try to define what exactly it is. And in any case, the more interesting part is not actually this class. I mean, here it's not trivial that it works, but in the end, it looks very similar to just Kunz-Krieger case. So the interesting class is really the dual class. And again, maybe at this point it makes sense to return back and recall what one had in Kunz's case. Yeah, this class. So what this unitary represents, it really represents that shift on the space of infinite words in n letters. Why is that? So we can think of elements of the orthonormal basis of this full Fock space as words in n letters. And then if you take tensor product, you can think of words in like going in both directions, to the left and to the right. And so what this operator then does, so it takes a word. So a word consists of, like, have two parts, one going to the left, one to the right. And this operator erases letter I in one word and immediately creates the same letter in the second word. So in the end, it just means that the whole word is shifted by 1. So in some sense, this operator is the operator of the shift, which is exactly our hyperbolic transformation, for which we can get this duality. So what we will try to do is something similar, but more commutative. So in our case, we will have not an alphabet consisting of n letters, but our letters will consist of modulus over our quantum group, and corresponding shift will correspond to multiplication or tensoring of modulus by another fundamental modulo in our category. So to see how it works, we have to recall how representation theory looks like. So this is the representation theory of U2. So for each, so remember how representation theory of U2 looks like. So for every spin, so basically you have representations of SU2. So for every n, there is a spin n representation. And plus you have powers of the determinant. So here the situation is similar. So you have representation of our n-dimensional fiber in our product system, and we have one-dimensional representations and their powers, which we call as determinant representation. And the fusion rules are as follows. So you can multiply representations by determinant on the left, on the right, up to isomorphism. This doesn't change, although the representations do change, but not up to isomorphism. But the main rules are these familiar sort of SU2 rules. So when you take sort of spin n multiplied by spin 1, you get spin n plus 1 plus spin n minus 1. But as I said, we're not in SU2, but in U2, so you have to remember putting determinants so on the left or on the right. So if you do this, then you can build out of this sort of this shift operator. So if you consider our full Fock space, consider almost the same full space, just forget about the vacuum, the zero part of the space. Then we have an operator from, so before we had like letters in, words in letters going to the left and to the right, but now we'll have two copies, basically because H1 is a two-dimensional space. So we have an operator going through from this space onto this space. So the main part is, as I said, it's basically the same thing. So if you think that you have a letter H1 in the left part of the word, and you move your letter from the left part of the word to the right part of the word. So this is like a quantum shift, but on the space of modulus over your quantum group. So you have to be sure that it works. So as an abstract operator, that's fine, but in the end we need elements of some concrete system algebras. And this is some computation. I mean, the precise formula does not matter, but what you have to be sure about that in the end, this operator lives in the Chapter algebra you're constructing. So it turns out that you can explicitly compute this operator. It's a somewhat ugly expression, reminding to some extent what Kahn and Henry did, but probably much uglier. But the important thing is that it really lives in the tensor product of the Chapter algebra with itself. So here, this AI's are creation operators acting on the left, RI's creation operators acting on the right, and phi is the operator of multiplication on each fiber by this number. So in the end, just by construction, you get a partial isometry in 2x2 matrices of the tensor product of Chapter algebras, and as a result, you get a unitary in the 2x2 matrices and the tensor product of Spimsner algebras. And so we have a homomorphism, again, from algebra functions on the real line vanishing at infinity, and 2x2 matrices now of Kuhn-Spimsner algebra corresponding to this transposed polynomial and to the polynomial itself. And this gives us a class. Okay, so now the main result is that indeed these two classes provide you with a duality. So for every temporary polynomials, this Kuhn-Spimsner algebras are KK-dual with dimension shift 1 and with duality provided by these two classes. So yeah, let me remaining 2 minutes, say a couple of words about the proof. I said that sort of quantum symmetry plays a crucial role here, both in the construction and in the proof of this result. So in the construction, I saw that the fusion rules for the symmetries were used to create this non-commutative shift map, and in the end, the small class delta. But how it appears in the proof? So it turns out that, well, one can ask, well, can one upgrade this result really to some sort of equivariant duality? And this doesn't quite work for reasons I won't have time to explain probably. But still, some sort of equivariance is still around. What turns out to be true is the following. So to prove duality, we have to compute some composition of morphisms of this sort. And we have to prove that up to a sign there's a plus minus ones. What it turns out that although each of these classes is not equivariant in the most obvious sense, if you take the composition, this class is naturally represented by something equivariant, so by an element in the equivariant KK theory. And the main result is, and the claim is that this composition is actually equal to 1 in this equivariant KK theory, not just in non-equivariant version. And it turns out that this is actually easier to prove than non-equivariant version. So it tells you more, but it's easier to prove. And the reason here is this technique based on monoidal equivalence, which goes back to Christian, employed. So we used. So it turns out that KK theory behaves nicely with respect to monoidal equivalence. And so to do these computations, you could actually go from a given quantum group to a monoidal equivalent one. And in this case, I said all these quantum groups are monoidal equivalent to UQ2. So you do this, and it turns out that basically all you have to do is just this particular case of the theorem where these polynomials, which kind of giving you some generalization of quantum versions of 3-sphere, and these quantum groups were just quantum UQ2. And the point is that still you have to prove it, at least in this case, but this quantum group is studied much more than all other quantum groups, and you have various techniques dealing with it. So this becomes more doable. Finally, let me say that in this kind of extreme case Q equal 1, we do get from all of these equivariants. So in particular, this implies that this three-dimensional sphere, just the classical one, is the self-dual in the U2 equivariant way. So I'll stop here.
Thanks very much.
Can you say a bit more about the equivariance? So for Q equals 1, you get equivariant?
Yeah.
And
why?
So what goes wrong?
Oh, it's very silly what goes wrong. But somehow, when we consider these two Kunst-Pimsner algebras, then the same quantum group is the symmetry group of this quantum algebra. But on one, it acts on the left, on the other, it acts on the right. And in quantum case, these are very different things, so you cannot just easily go from left to right. So this is a very, in a way, silly reasons, but it's not quite obvious what to do about it. In the extreme case, when our quantum groups are actually classical groups, of course, there is no difference between left and right action, and everything is nice. So in this case, already the original class is equivariant, and the proof shows equivariant.
So maybe just one more general question. So if you change dimension from 2 to 3, then you cannot expect any universality probably, but for specific polynomials, you get UQ3 for very specific ones, or?
No, I think if you have UQ3, you cannot deal with principal ideals. I think you need several.
Oh, you need.
You need an ideal with several generators.
Right.
But yeah, I mean, we're actually trying to do not exactly this, but studying this higher rank case. But generally, I said these algebras for subproduct systems, they are fully understood in very few cases. So, apart from these kind of cases, the ones which were fully understood before, only the ones corresponding to ideal generated by monomers.
If there are no further questions, let's thank Sergey again.